Okay, so the previous lecture we finished with the basis condition and basis systems and orthogonal systems in Hilbert space. Yeah. So the topic of lecture today will be compact and pre-compact sets in metric spaces. Set M in metric space is compact if for any sequence xn from set M there exists subsequence x and k which is converged such that biometric in and this element x is to belongs to M. Some remark in topological spaces such compactness is named sequentially compactness. But in metric spaces, it is coincide with classical definition, classical topological definition. Via coverings. From any coverings with open sets, it is possible to choose the finite subcovering. Yes. For any open sets covering of M, it is possible to find finite subcovering. Such that M lies in okay. So because it is coincide, I don't prove this fact. I don't want to go into topology. Because it is coincide, we use it as definition. We can say it as metric compactness. Compactness in metric spaces is just a sequential compactness. Okay. So then I remind that infinite dimensional spaces, compact sets is bounded and closed. but in functional analysis, we in general will study the infinite dimensional spaces. So we must find a new criteria of compactness in finite dimensional normal space and for some metric space. So new definition that X through metric space and we have subsets Y and M in this metric space. Then we say that Y is epsilon network for M if for any X from M there exists Y small from Y capital such that this X belongs to the ball with the center Y and radius epsilon. In other words, M can be carved by balls with centers Y small, radius epsilon, Y small belongs to Y capital. And very close notion for this. Set M in metric space is totally bounded if for any positive epsilon there exists finite epsilon network. Then for applications, the notion of compact sets is sometimes is very strong notion. So it is useful to find more weak notion, but very closely connected with the compactness. For example, what is the strongest of this definition? Any subset of compact set may not be arbitrary subset of compact set, maybe not be compact. So the question, how we can make this notion more weaker that it has that this property preserves for the subsets. So definition, set M in metric space is precompact if its closure is compact set. Compact set. Some remark, very useful instrument. You can see that the definition of the precompactness is not used the sequences, but the instrument of sequences is very useful and very simple in metric spaces. So the remark will allow us to work with sequences when we try to understand is set is compact or not compact. or pre-compact or not pre-compact. In metric space, X rho for pre-compactness of M, of set M, is necessary that for any sequence in M, there exists fundamental subsequence. And in incomplete space 6 rule, it is sufficient. Need we discuss this property more in more details, or it is clear? Because if you find how we can show that set M is not pre-compact. If you find a sequence for which we can't find fundamental subsequence for, due to this remark, we can conclude that our set is not pre-compact. And if we work in complete space inverse, if we can show that for any sequence we can find fundamental subsequence, then we can conclude that our set M is complete, is pre-compact. Okay? So some example. Let's consider unit ball. Unit ball in L2, small. It is, of course, bounded. And closed. Unit closed ball. Bounded and closed. But let's consider our basis elements, sequence of basis elements, standard basis. EK equals of sequences on one cut place it is 1, other coordinates are 0. We can see that the distance between EK, EG, which is just the norm, and it is equals square root of 2 if K is not equal to G. So for any different elements, the distance equals to square root of 2. So there are no fundamental subsequences. So the unit ball in one of examples of bounded and closed set that for infinite dimensional space L2, the closed and bounded set is not compact. Let's prove one lemma, so-called Riesz lemma of an epsilon perpendicular.
Sorry.
What?
What does the bounded means here? Does it mean the totally bounded? The united ball in L2.
No, unit ball is bounded. That it means that for any x from unit ball with center I ball, let's write, with center 0 and radius 1, for any x from this ball, the norm is less than 1, so it is bounded.
Ah, okay.
And by definition of our balls, it was a simple exercise. The closed ball is really indeed closed set. Closed set. Okay.
Okay.
So let's follow it. Rees lemma. And in Russian literature, it's named as epsilon perpendicular. Let X is a normed space. X0 is non-trivial. A closed subspace. For any epsilon from 0 to 1, there exists X epsilon. It does not belong to X0, such that first the norm of X epsilon equals to 1, and distance from X epsilon to X0 less than this number. And this by definition equals infimum of difference of norm X epsilon at X0 small from the XL. This is called, what this formulation is called. So proof. Take arbitrary X from which does not belong to X0. Such X's exist. Because X0 is non-trivial closed subspace. Then D is closed, the X0 is closed, then define dist between X and X0 as number D, and it is positive because X is not from X0 and X0 is closed. Then again, we can take there exists such Y from X0 such that D less than X minus Y less than D by definition of infimum. Let's define X epsilon as we want to obtain in theorem as such vector. Of course, by this definition, the norm of X epsilon equals to 1. Yes? And the distance, let's try to check for any x0 from x0 small. Let's calculate x minus x epsilon minus x0. So put our definition of x epsilon minus x0 norm we can take away this number out of the norm, and the norm we have such formula, such expression, and we can see that this is some element from x0. Yes. So let's try to find some estimation. What we can say about this factor? From this, it follows that it is not less than this factor. Yes. And for this, because for the second factor, we can obtain that this is not less than d, because this distance between our vector x and some element from x0. So it is so we obtain our inequality, yes, and we obtain it for arbitrary x0. So for infimum, we can obtain the same inequality. So this proof is finished. Corollary. Let X is normed space and it is infinite dimension. Then unit closed ball, it just doesn't matter, open or closed, well, take closed. The unit closed ball is not compact. And it is not pre-compact. Proof. First, take some element x1 such that its norm equals to 1. Construct linear span define it x1 linear span of its element, one-dimensional space. Well, because it is finite dimensional, it is closed. So by Riesz lemma, there exists x2, the norm of x2 equals to 1, and the distance between x2 and the whole space x1 for fixed epsilon from 0, 1. So define x2 is linear span and to know that the distance, not distance, the norm between x of difference x1 and x2 not less than 1 minus epsilon, and etc. If we construct x1, x2, xn such that the norm of x e equals to 1 and the pair distances not less than 1 epsilon for e not equals to g. So construct xk the linear span it's finite dimensional space. So it is closed. Then exists by lemma the next element yk not k. I finished here as n, so just correct it for n. N. So exists the next element with index n plus 1 such that distance between this element and subspace x and capital not less than 1 minus epsilon. So from this implies that the norm of differences not less than 1 minus epsilon for k equals 1, 2, n. So by induction, we construct sequence xk, infinite sequence, from our unit ball, the norm of any element equals to 1. Here I omit it, so let's cover. And here we have our sequences. And because the distance between any different elements is not less than 1 minus epsilon, so there are no fundamental succession. So we understand that in infinite dimensional space, norm space, the unit ball is not compact, but it is bounded and closed. So we must obtain something criteria new for infinite dimensional space. So first I prove so-called Hausdorff criterion. Theorem. Hausdorff have two F or one F. I forget. Let X rule complete metric space. Set M in X is pre-compact. If and only if M is totally bounded. Totally bounded. So for any epsilon, there exists finite epsilon network. Moreover, we can show that it is incomplete space is criteria, but again, for non-complete, it is necessary, but incomplete, it is sufficient. This formulation. For pre-compactness, it is necessary to be totally bounded, and for complete space, it is sufficient. Proof. Let's prove it. Let's first we prove it in this direction. Let's prove our statement in this direction. By contradiction. We'll show it by contradiction. Let M is not totally bounded. Then there exists epsilon for which doesn't exist epsilon network. Finite epsilon So let's take x1 from M. So it is not epsilon network. So exists element from M such that the distance between x1 and x2 not less than epsilon. The set x1 x2 is not epsilon network. So exists x3 from M, not epsilon network for M. So exists element x3 from M such that the distance between x3 xi not less than less than epsilon for I equals 1 2 etc. If we construct x1 x2 xn from M such that the pair distances not less than epsilon for E not equals to G, then the set, we have finite elements. Finite elements, it is not epsilon network. So exists xn plus 1 from M such that the distance between this element and previous elements xi not less than epsilon for I equals 1, 2, comma n. So by induction, we construct sequence xk with property that the distance between xi, xg not less than epsilon, sp not equal to g. So M is not precompact. Contradiction. The first part of our theorem we prove. Second part, the inverse direction. The inverse direction. So M is totally bounded. Let's, okay. Again, inductive methods. First, take epsilon 1 equals to, take first arbitrary sequence from our set M. If we want to prove that it is precompact, it's sufficient to show that we can construct a fundamental subset. So take epsilon 1 equals 1 over 2. Then there exists for M, there exists 1 over 2 network. Y11, Y1, and 1. The index up is the number of our step, and index down is the numbers of our net. We use the countable steps, countable number of steps. So M sequence Kyle from M, and M lies in covering of balls with centers of our network, radius 1 over 2, and it is finite union. Yes, finite union. So it is countable. It is finite covering. So let's define. So we can say that there exists ball with some indexes E1, 1 over 2 contains infinite subsequence. Infinite subsequence from first sequence xk. So let's designate it. It as x1k. Second step. Okay, right. First step. Second step. And then we can make induction. Take epsilon equals 1/4. For M exists 1/4 network. And as I say, the index up is the number of our step. So this sequence x k1 infinite, it lies in the finite union of balls with the center of our network from the second step, but radius 1/4. Again, it is countable. This is finite covering. Again, this ball with some center I2, radius 1/4, contains infinite subsequence from x k1 k. So let's designate it. So we can construct by induction. Let's say we need the step of induction. By induction, we can construct a countable set of subsequences. First, our sequence for initial subsequence, then first subsequence, second subsequence, and by induction, subsequence with number m, and so on. Okay. And what is property of this subsequence? What is the distance between x from the sequence for now with number m? It is subsequence which lies subsequence x k m lies in ball with previous indexes m minus 1. It is infinite subsequence which lies in one ball. And radius equals 1/2 in this. So from this, we obtain that it is less than 1/2 m minus 2. Yes, because the radius of ball in which lies this subsequence is 1/2 power m minus 1. So they may be diametrically by triangle inequality. Put here this center, and we obtain that the distance between these two elements is 1/2 power m minus 2. So consider so-called diagonal subsequence. So it is fundamental. So M is precompact. In this direction, we use the property of completeness of space. Because precompactness, it is not in general situation for arbitrary metric space. I again repeat this remark. In general situation, the precompactness is not equivalent to the possibility of choosing the fundamental subsequence from any sequence. But for the complete subspaces, it is just the equivalent notion, as I say in the remark. So it is finished our theory. So is it clear? So some subtopic criteria.
I'm sorry, could you explain again? Could you explain again why this subsequence was contained in another in a chain?
You want to explain this? Yes. This
No,
property?
no,
not this.
Above, the row above. xk containing xk1, containing xk2. Oh, no.
Because
Yeah.
let's repeat here. The first step, for example, we have finite network, yes? So we have finite covering of M, and our sequence lies in M. So our sequence is covered by finite numbers of balls. Yes?
Yes.
It is infinite sequence, and number of balls is finite. So exists one ball which contains infinite subsequence by Dirichlet principle, for example.
One ball contains
exists one ball which contains infinite subsequence from our sequence K. And this subsequence I designate its x with index 1 up. Yes? And then repeat. We take next step. We take smallest epsilon. For example, I take 1/4. And for this epsilon, we again have a finite network. So our sequence x1 lies in M, yes, because it is subsequence of, it is again lies in M. And this is a finite covering of M. And we again have a countable set elements in this sequence.
Okay.
And finite numbers of balls, So exists
I understand
on
now.
the second step, which contains again infinite subsequence from the previous sequence. So on each step we choose a new subsequence. Yes, but we take epsilon smaller and smaller. So we have the nested subsequences Yes,
Yes, yes.
with this property. This property is important. Yes, for fundamentality.
Yes, yes. I understand now. Thank you.
Okay, yeah, okay. Oh no, don't hesitate to ask question. Here minus 1. So new topic, subtopic. Yes, it is not a new topic, it is subtopic. So we see that again repeat the logic. We see that good spaces is closed and bounded, which, for example, unit balls in infinite dimensional spaces, norm spaces, is not compact set. But we have a good criteria, Hausdorff criteria, which says that for complete metric space, the precompactness is equivalent to the totally bound. And totally boundness looks like in the topological spaces. It is totally bounded. There existence for any epsilon of finite covering by balls with the fixed radius. Yes. And with this instrument, we can show the criteria for some concrete norm space. So criteria subtopic. Criteria of precompactness in concrete norm, sorry, not norm space. But I need additional instrument, so-called Dini lemma. Let K is a compact set. Fn is continuous functions on K, and for any x from K, it is real valued functions, f and kx monotonically tends to f of k is continuous function 2. On K2. Then the statement of theorem Fn tends to F uniformly. So this arrow means that it is non-decreasing, non-increasing. Non-increasing. Is it known theorem or not? Or we need to prove it? Usually, in calculus, it's used for functional series with non-negative terms, and so for this situation, the lemma Dini changes the monotonicity. If we have to consider such functional series and UK is non-negative, then you can see that SK Sn, which is partial sum of UK, is non-decreasing. Yes, the direction of monotonicity is not important, because you can multiplicate your sequence Fn on -1. The converging is not spoiled, but it's changed the monotony. So again, I repeat my question. Do we need to prove this lemma or it is known?
Maybe prove it.
Okay, let's prove it. It is not difficult, but useful. Let's take epsilon positive. What we can say for any x, what, there exists number n, and let's capital, which depends on x and epsilon, that for any n not less than this n, we have fn x minus fx. We have monotonicity, so it is greater than 0, yes, and then less than epsilon. This is inequality from this property. Yes, function fn minus f is continuous. So there exists such neighborhood of x that for any x prime from this neighborhood, f n x prime minus f x prime, we have the same inequality. Because this again function is continuous, so the inequality valid in some neighborhood. Yes. Consider, of course, k lies in row. It is equal. Yes, we don't see nothing outside our comp. So we have covering of k. Of k. It is compact by condition of the lemma. Yes. So there exists finite subcovering. Once again. Xi small. Oh. Let's method I from 1 to m sum xy. Then take a new n, that's m. It is maximum of these numbers. Maximum of I with 1 to small m. Then you can take this thing, this line, for any small n that is not less than capital N, we have this inequality. And then we immediately obtain that for n not smaller than m capital, for any x from k, that's all. We have a uniform convergence for any k, for any x from k. Okay, yes. So first theorem for criteria for concrete matrix space, norm space. So theorem 1. Let 1 equal or less than pi, pi is not infinite. Set M lies in LP is Rare compact if and only if two properties. A, M is bounded, and B, for any epsilon there exists N which depends on epsilon, such for any x from M they're both conditions. Available. And this is conditions in jargon, so-called tails is uniformly small. Tails of the series, yes, it is uniformly because this index n is common for any x. So it is intuitively can be described as all infinite part of our set M is very small. The main part of elements lies in finite dimensional space, which is defined by this number n. So all provements will be in one scheme. In one direction, we use Lemma-Dini, and in other direction, we use Hausdorff criterion. Okay, so proof. Proof. First, this direction. First, consider closure of M is compact. Yes. The norm is continuous function. So there exists maximum. Let's define this constant C. Then we immediately obtain that for any x from M, the norm of x is less or equal to C. And then consider functions f n on the closure on our compact, it's easy to understand what set of functions we must consider. It's just from the definition, from formulation of theory. What we can say about this function? Of course, it tends to the zero function as n tends to infinity. Yes, because it is tail of converging series. Any element lies in LP small. And second, it is continuous. It's continuous because it is norm. It is norm, but not all of not all element X. But it is the norm of element which with first coordinates equals to 0. So we have monotonic sequence which tends to the continuous function. Yes. So by Dini lemma, we conclude that the sequence tends to the 0 uniformly on M. And of course, it is tends to the 0 uniformly on M without closure. And this is just item B. Is it clear? So let's consider another direction. By B, there exists N. We'll take epsilon, positive, depends on epsilon for any x from M. The tail is small. Define xn as element x1, x2, xn 0, 0, 0, and Zn defined as 0, 0, 0, xn plus 1, and so on. These elements lies in space LPN, yes? And for this, we can say that the norm less than epsilon. What we can say about our set M intersected with LPN? Our xn lies here. It is bounded set by A and lies in finite dimensional space. So it immediately obtains that all xn while x lies in M is precompact set because it is bounded and finite dimensional. Is precompact set. So there exist elements, finite exist finite dimensional. Oh, not dimensional, finite epsilon network. yn, y2, ym. How these elements looks like? They lies in LPN and infinite dimensional or infinite dimensional part of LP in LPN. So each LK looks like EK1, EK2, EKN. Yes, for any K. But we can for any YK we can extend it or embed it into LP. So YK tilde looks like the same first coordinates and then put infinite numbers of zero. So it is lies an LP. So let's take any x from M and try to understand why we can take why we can make this norm is small. Xn minus yk plus zn less than maybe here, but on the next step I can take not weight elements. And by triangle inequality. This is small less than epsilon by choosing n, yes? N. And this is small by choosing number k. So we obtain that it is two epsilon network. And it is finite, have m elements. So M is precompact. We construct finite network. LP is complete by Hausdorff criteria. Okay. So it is finish of our first theorem. Second theorem, maybe I take some time from the seminar, but not a lot of time it take. About space of continuous function on the interval. But I start with definition. Set M in continuous function is equicontinuous family of functions if for any epsilon positive there exists delta positive such for any xy which lies in AB with the property we obtain that for any f from M. This is important. Uniformly for the set fx minus fy less than epsilon. Let's some remarks or some examples on this definition. Set M have only one function. Only one function from space of continuous functions. What we can say about the equicontinuous of this set? What means the definition of equicontinuous? Is the same of uniformly continuous. Because we have only one function, so one function. So this is quantum is not important, but important for any x, y lies in interval AB. So it is uniformly continuous, but any continuous function on the interval on the compact is uniformly continuous. So it is automatically. Is true. On AB on any compact. The same you can say the same is true if M contains finite number of functions. Because for any functions you have delta 1, delta 2, delta M, then you take smallest delta. So more interesting situation. More interesting situation. When M has infinite many functions. But we discuss the examples on the seminars. And one more remark, you can define one can define equicontinuity T whose family M from CK when K rho is compact metric space. So interval AB is not general situation. You can consider arbitrary compact K, but with metric rho, here absolute values of elements you must change on metric. So only change. So change x minus y through x y. Then let's formulate theorem, and we prove after break. Theorem 2. So it is so-called Parcella-Ascoli theorem. Parcella-Ascoli. Italian mathematicians. Ascoli theorem. Set M in CAB is pre-compact if and only if, again, to both conditions. A, M is bounded. Second, B, M is equicontinuous family. Is R valid. Both, so it is R valid.